Remember from your CCNA studies that we had a 7-layer OSI model. It began with layer 1, the physical layer, and that was followed by the data link layer at layer 2, and we said that's where Ethernet switches would reside, and we had the network layer at layer 3, that's where routers live, and up at the transport layer, layer 4, this is where we have TCP segments and UDP segments, and that was followed by the session layer and the presentation layer and the application layer. And in this video, we want to focus on the headers found in various TCP/IP protocols. We know that TCP/IP is not a single protocol, it's a suite of protocols. It includes IP, it includes TCP, ICMP, UDP, and others. We want to take a look at some of the headers because the behavior of those protocols is really the foundation of the routing topics found throughout this video course. Let's get started by taking a look at the header of an IP version 4 packet. We see that it has several different fields. Let's point out a few of them. To begin with, there is a 4-bit version field, and this version is going to indicate that this is an IP version 4 packet. In binary, what is a 4? It's 0100. That's what's going to be found in the version field of an IP version 4 packet. Also notice the type of service or the TOS byte. We have 8 bits in this field, and typically we use the 6 leftmost bits in this field to indicate the priority value of a packet. This is a quality of service topic. We're going to use those 6 bits to mark a packet with a differentiated services code point value. And that can indicate that one type of traffic, for example, voice over IP or video, might be more important than another type of traffic, like network gaming traffic. Next, notice the TTL, the time to live field. This is a value that gets decremented every time a packet passes through a router. And if this value ever reaches 0, the packet's going to be dropped. And this is a good thing. This can help prevent routing loops. Also notice the protocol field. This is an 8-bit field, and it says what kind of data is encapsulated inside of this IP version 4 packet. Commonly, we'll find a code representing TCP or UDP, layer 4 protocols that are encapsulated inside of this layer 3 IP version 4 packet. And with IP version 4, the IP addresses are 32 bits in length, and we've got a source field and a destination field for the source and the destination IP version 4 addresses. Let's now contrast that IP version 4 packet header with an IP version 6 packet header. Notice that an IP version 6 packet header is a bit more efficient. We don't have as many fields. We still have a version field. This time it's going to indicate version 6. That 4-bit field is now going to say 0110. That's a 6 in binary. There's a traffic class field, which is very similar to the type of service field that we had in an IP version 4 packet. The flow label field is a 20-bit field, and it can be used to tell a router to use a specific outbound connection for a traffic flow if a router has more than one outbound connection. And by having all of the packets in a flow using the same outbound interface, that's going to reduce the odds that packets might arrive out of order. The next header field is very similar to the protocol field in an IP version 4 packets header. It's telling us the type of header that's encapsulated inside of this IP version 6 packet. The hop limit field, that's the replacement for the time to live field, and we've got source and destination fields. Of course, this time with IP version 6, the addresses are longer, so instead of being 32-bit fields, they're 128-bit fields. And residing next to IP down at layer 3, we also have ICMP, Internet Control Message Protocol. And there's a lot of debate in the industry about where does ICMP fit into the OSI model. Some people will say it's layer 3, some people will say it's layer 4. Generally, ICMP is considered to be a layer 3 protocol, but some of its messages are based on layer 4 events. And one of the most common things that ICMP helps us out with is pinging. When we do a ping, we're sending out an ICMP echo message, and we're receiving in response to that an ICMP echo reply. The ICMP header does not have all that many fields. We have a type field, which says what kind of ICMP message is this. A type 0 is an echo reply message. A type 3 is a destination unreachable message. A type 5 is a redirect message. A type 8 is an echo request message, as just a few examples. And notice the code field that can further define the ICMP message type. As an example, the destination unreachable message has 16 different codes. We've got a checksum field for error checking, and the rest of header field is a 4-byte field, and what lives here is really dependent on the ICMP message type. And there are several different types, but for the route exam, based on the route blueprint, there are 2 specific message types I really want you to pay attention to, and those are the destination unreachable type and the redirect type. First of all, destination unreachable. Let's say that a packet goes into a router, and the router does not know how to get to the destination address on that packet. What the router can do is let the sender know that it has no idea how to get to the destination by sending back to the sender a destination unreachable ICMP message. Next, think about a redirect message. Maybe we have a host that has information that says, in order to get to this destination network address, we should send our packets to this next hop IP address. However, network conditions might change. And if there's a different next hop IP address that host should be using, the original next hop router could let that host know by sending it a redirect ICMP message saying, actually, you should be using this next hop address. Now let's move up to layer 4 and take a look at a TCP header. We've got 16-bit fields indicating the source and destination port numbers. The sequence number and the acknowledgement number fields help give TCP its reliability. For every segment that a TCP sender sends, it should get an acknowledgement back from the receiver, acknowledging that that traffic was received and requesting the next sequence number. And we know that TCP can use a sliding window. And there's a window field, it's 16 bits in length, and it tells us the number of bytes that a sender is willing to transmit before it needs an acknowledgement from the receiver. And finally in this video, let's take a look at the header of a UDP segment. It doesn't have many fields at all. It's very efficient in terms of overhead, and as a result, when we're sending voice over IP or we're doing a video conference, those voice and video packets, they're typically encapsulated inside of something called RTP, the Real-Time Transport Protocol, and that's a layer 4 protocol, but it's encapsulated inside of UDP, another layer 4 protocol, instead of TCP. We've got source and destination port fields, much like a TCP header. We've got a length field, and optionally, we can have a UDP checksum. And since UDP is used to carry voice traffic as an example, a design concern we sometimes have is latency. And latency is delay. How long does it take to get from point A in the network to point B in the network? And what we can do for high priority traffic that might use UDP, voice over IP traffic as an example, we could use a quality of service mechanism such as low latency queuing, LLQ. And what LLQ is going to do for us is carve out a priority queue from the buffer space available in a router's output interface. And we can put our high priority traffic in that priority queue, and we can still guarantee bandwidth amounts for non-priority traffic, but we put those traffic types in non-priority queues, and as a result, the voice gets to go first. Think of low latency queuing as being analogous to a carpool lane. In a lot of major cities, you might notice that the leftmost lane in a highway is designated as a carpool lane. There might be diamonds in the lane, and there's a sign that says if maybe there are 2 or more passengers in the car, you get to drive in this carpool lane. You get priority treatment because you are a special type of traffic. That's what low latency queuing does. We can say this is a special type of traffic, and as a result, we're going to put it in this priority queue. But it's not like the Autobahn. It's not like the German highway with no speed limit. There is a speed limit on that priority queue so that we don't starve out other traffic types. We say, yes, you get to go first, but up to a point. We're not going to starve anyone else out. And that's a look at the headers found in 5 of the more popular protocols in the TCP/IP suite.